David over 50 times in the last several months. As you can understand, the topic has been very timely, and everybody has been suffering through this pandemic, and we all have been trying to figure out how we can protect ourselves and the buildings that we occupy. So David developed this webinar to inform everybody about the steps that they can specifically take within their building systems. We have actually implemented some of these strategies within our own buildings, and also have helped our clients implement some of these strategies that have been advocated by ASHRAE and also CDC. Dave's been a part of Allen Tree for over 27 years. He's a mechanical engineer and has a tremendous knowledge about the subject. So without further ado, I'm going to turn it over to David. There is a chat box where you can ask your questions, and during the webinar, David or myself will try to answer them. If not, we'll wait till the end if we don't have the opportunity to answer your questions. So thanks again, everybody, for attending. And David, here you are.
All right. Thanks a lot, Zach. So yeah, this seminar is actionable steps using MEP to reduce transmission rates. It is good for 1 credit hour HSW through AIA. They will look at, we do have to maintain a log of when you logged in, when you logged out, and you got to be here for the bulk of the time to get the certificate. So since everything went remote, they've added that requirement. Course description, acknowledging that COVID-19 is primarily transmitted as an airborne virus. The course will review how can MEP design help reduce those risks. We provide a base understanding of how we catch viruses, including COVID-19, and review actionable items for reopening and long-term strategies for pathogen control. At the end of this course, participants will be able to understand the 3 primary transmission methods of COVID-19 and typical preventative measures, understand infectious dose and viral load, understand short-term HVAC approaches to reduce transmission to include ventilation and filtration, understand long-term solutions for pathogen control, including air sanitization, and understand how other MEP design contributors to pathogen control. We will give a short break at the end of each little section here to see if there's any questions. Otherwise, you put them in chat. I think Zach's going to try and monitor the chat, and we'll go from there. So the first item we want to hit is kind of a side note to COVID-19 is our buildings have been sitting more than 3 months now. But Legionella is by far the biggest waterborne bacteria that we have in the U.S. And it grows in ambient temperatures, which is what we have in the water where it's been sitting, stagnant water. So anytime it's been sitting over a week, you're supposed to flush your systems. This link here from the CDC describes how to flush them. And you got to be really careful, as you go back into buildings that they are flushed properly, and as you go back into floors. So if the building's been occupied, but floors 2 through 8 haven't, then you have to flush each of those floors, and watch out for long runs to like ice makers and things like that have very low flow rates to make sure that they're flushed out properly. So the reason we're talking about this is obviously some of these items here is we have to assume that at least some of the occupants that come through our building sooner or later are going to be carriers. 30% of the carriers are asymptomatic and never get tested. 44% of transmissions happen by asymptomatic people or pre-symptomatic people. So sooner or later, you're going to get someone in your building once you open up that's going to have it, doesn't realize they have it, and may be transmitting. So that's what we're looking out for. So we need to treat as if every person may have it. There's 3 transmission methods, and we're going to go through and describe each one very briefly, and then we're going to hit on how you address all 3 of them, and we're going to spend most time on aerosols. The first transmission is fomite transmission. That's touching surfaces. So for touching surfaces, we're looking at touchless systems, hand sanitizer, cleaning things, stuff like that. Now the CDC did put out back in May that this isn't thought to be the main way the virus spreads. It's still a main focus of what people are doing, but it isn't thought to be the main way the virus spreads, and we do need to spend much more time on some of the other transmission methods to get this under control. So we have 2 charts over there on the right-hand side about how long COVID lives on surfaces. And you'll see up there on the first item, in air, it lives up to 3 hours. So that's what we're going to be talking about more than anything else. But then on plastics and stainless steel and things like that, it lives up to 3 days. And since we're not always going to be talking about COVID-19, there's another chart down there at the bottom right, and lists some other pathogens. And you'll see Salmonella, for example, lives up to 4 years on surfaces. So depending on what we're talking about, things can live quite a while on surfaces. And everyone's relatively familiar with, the items we've been doing to address the film mite. Droplets, this is close contact person to person. This is the primary transmission method. This is why we do 6-foot spacing. This is why we do the masks, the screens, orientation at desks, room limits, things like that. And the reason is, the chart over here on the right is this is based off the SARS virus, how far droplets carry. So if you cough or sneeze, or if you're talking, that they're going to be that 3 to 6 feet area. So that's what we're trying to protect from, and that's why we try and do that spacing and masks when we can't do the spacing. The far right column shows droplet nuclei. So, and you saw 160 feet there. So that study, basically, the droplet nuclei filled the whole area of that study. That's why it says 160 feet plus. So what are the droplet nuclei? So this came out a couple months ago, back in towards the middle of July, open letter to the WHO, basically pointing out that the WHO and the CDC are kind of, at that point in time, we're not paying enough attention to this issue, and that most of the super spreader events were aerosol or droplet nuclei versions. So, it was not a mask-related issue of being too close to people. It was going airborne and filling spaces over larger distances. So what we're looking at is when you're sitting at your desk working, or you're walking around or whatever, and if you happen to have the virus, you're going to be expelling those virus particles, and they're going to come out as large droplets and smaller droplets. So you're going to have the virus encapsulated in water and mucus, and as it travels, it's going to start to evaporate. If it evaporates before it comes in contact with the surface, before it falls out of the air, then that droplet becomes a droplet nuclei, or virin, or aerosol, or any one of those many terms that are being used. And basically, at that point in time, it's the same weight as the air. So it's going to travel around in the air. It's not going to fall out. It's just going to travel around until it gets filtered out or dies off. And what we have to watch is the viruses that are, still can survive in that form. And again, if you go back to the original chart we were looking at, COVID-19 can survive up to 3 hours, but not all viruses do. Ebola, for example, which is one of the reasons it was easier to control Ebola dies off instantly in this form, so it does not survive. So it was never an airborne risk. As we increase our activity level, we increase the amount of virus particles we expel. So we start off, if we're just sitting at our desk, not talking, not doing anything, we're around 30 particles a minute that we're expelling. If we start talking or singing or exercising, that rate goes up. If we cough, it's a couple 100,000 virus particles. If we sneeze, it's a couple 100 million up to a couple 100 million virus particles. So the more we do, the more we're going to expel. Now the issue that we have to watch is, it's not that, if I get exposed to, I bring in a couple virus particles, I get exposed, I'm passing someone in the park, I'm not going to catch the virus that way. I have to reach what's called an infectious dose level. So the infectious dose level is kind of still up in the air on this, but it's more than 10, and it's less than 500 million particles. The best guess seemed to be around 1,000 particles of the virus is what it needs to take to get the virus. So if you're talking to someone, or you pass them in the park, if they're only expelling 50 particles a minute, it's going to be very hard when you pass them for you to catch that virus. You have to be around the person. It's usually related to the time exposure of being around people. The other notable item is the viral load. So basically, viral load concept is the more virus particles you bring into your body, the more severe case of the virus you're going to get. So if we can reduce the amount of virus particles, hopefully our goal is to reduce them to where you don't catch the virus, or you catch a much less severe case of the virus. So that's what we're looking at. Those are two big concepts that we need to understand what we're trying to do with HVAC. And there's two case studies that back up, well, there's lots of case studies, but we're going to go over two case studies that back up the virus being transmitted as an aerosol. So this one goes all the way back to March 10th. And it was one carrier, and this was a choir practice in Washington State. And there were 61 people over a 2.5-hour practice, and they didn't move around a whole lot. They ended up producing 52 new cases. and there was no physical contact reported. And so basically this one pointed to an aerosol version. And one of the reasons that this one was a super spreader event is because when they're singing, the carrier himself or herself, whoever it was expelling a lot more virus particles because they're more active. And then the people in the room were also breathing in a lot more virus particles because they're more active and they're breathing heavier as they sing. So that was, this one really pointed to an aerosol event. They didn't touch, the same item enough for it to be fomite, and they weren't close enough to each other for it to be by droplets. The second case study we're going to look at is a South Korean call center, and this is back in February, March, and this is a 19-story building. Sorry, I saw a chat item pop up there. 19-story building. 811 employees worked for this call center over 3 floors, and there was 97 cases confirmed over those 3 floors. And 94 of them were 97 in the building, 94 of them were on the same floor. So what the CDC concluded on this was the duration of the interaction was likely the main factor. So the people going up and down the elevator weren't the ones infected. It was the people that worked in the same space with the same system over a prolonged period of time. So maybe they were bringing in 50 or 100 virus particles an hour, but over the course of a day or two, they brought in enough virus particles to get sick. So that's what we're looking at. And you can see most of those blue seats are all up on the top there in the same area. There's a couple people on the other side, but it was really the people that were around the same person in the same time for an extended period of time. So that's our risk we're looking at. And that's when we're talking, office buildings, churches, any area, restaurants, things where we're going to be hanging around in the same spot for a prolonged period. That's where we have to look at the HVAC and worry about what we're doing. And most of these cases are going to be inside. Outside, the ventilation is a little better unless you're really on top of each other. And that's usually outside. It's more a droplet transmission where you're really too close to people. If you can keep your distance outside, you greatly reduce that risk. So what are we going to try and do? We're going to try and reduce the number of virus particles in the space. We're going to try and reduce that exposure of people inside the space to below that infectious dose level by reducing contaminants from one person reaching the other person by either diluting, filtering, or killing off the viruses and bacteria, and in some instances controlling the contaminant path. So we have actionable steps. The most actionable steps is going to be increasing outdoor air, the filtration level, and then air sanitization. Those are the 3 that we actively look at as we're doing this. The ones that are a little more on the side, but do contribute a little bit, is going to be humidity control, the contaminant path, and then I don't think we're going to hit circadian lighting today, probably. So our typical commercial system, when we look at our buildings, what we're going to be looking at, whether we have an office building or a retail space or whatever it might be, most of our buildings, if they're designed to code, they're going to have a system similar to this, and it doesn't matter whether this is an air handler on the floor or a rooftop over a single-story building like we're seeing here. Most of the time, we're going to be bringing in about 15% outdoor air, and we're going to have typically a MERV 8 filter as kind of a baseline filter that we would have. And that 15% outdoor air means we're also going to be exhausting 50% of the air. And so if this is our carrier over here on the right-hand side, and we're bringing the virus in here, and we're going to exhaust 15% of the virus particles, and we're going to bring in 15% outdoor air, then we're going to capture 11% of the virus particles. And this is based off a swine flu study. And what is convenient for the analysis is the swine flu and COVID-19 are roughly the same size. And most viruses are roughly the same size, actually. Most airborne viruses are roughly the same size. So we're going to capture an additional 11%. So if you take that 15 and 11 and you multiply them, you end up with a 75.6% pass-through rate. So we're going to be about 3/4 of virus particles are going to get through each pass, and about 1/4 is going to get captured or exhausted out. So our air is going to go through our system 4 to 6 times an hour. So 4 to 6 times an hour, we're going to be pulling off roughly 1/4 of the virus particles. So that's kind of our baseline of where we started. So we want to see from there what we can improve. So the first step, the first recommendation is to increase the ventilation rate. And so we're going to, the goal here is we're going to dilute the indoor contaminants. The codes over the years we're primarily focused on energy. And as such, we went from in 2006 in a common office, we were looking at 20 CFM per person. Oops, sorry, jumped ahead there. And now we're down to about 5 CFM plus 0.06 per square foot. So what you see there is that the density of the office really determines how much air we end up getting. So the higher density spaces where we have benching and things like that, we're down now to 11 CFM a person, and in conference rooms, we're down to 6 CFM a person. So that's kind of where we stand. And that's before we look at occupancy control. So what we're going to do, occupancy control is, again, another energy method. So we have CO2 controllers that are looking at how many people are in the space and varying the ventilation accordingly. Or they have, we have occupancy control that either just turns on and turns off as we come into the building. So the 3 steps that are recommended, the first step is we're going to turn off the CO2 controllers. So if I have a CO2 controller that's trying to monitor the number of people, and that's reducing the ventilation, I want to turn that off and go and just do an occupied, unoccupied schedule. So if I had a CO2 controller and it said, okay, you're roughly half occupied, and so therefore we're going to run half the ventilation. In our case, we would reduce from 15% outdoor air to 7.5%. So we wouldn't turn that off, so that instead what it does, as soon as you come in the building, it goes, okay, you're occupied, we're going to go to the ventilation, and we're going to go 15% right out of the gate. So that helps out right there. The second is going to increase our outdoor air levels. So we're going to push them up as far as we can. There is no specific level you're trying to get to, just as high as you can. The recommendation, as long as you can maintain your temperature and humidity, you want to push that number up. So dead of winter, dead of summer, it's going to be hard to do. You can't go as far, but on the shoulder seasons like right now, you ought to be able to get up to 50% or more outdoor air on, in our occupied buildings. The last thing we're going to do is we're going to run longer occupied times. And this is where the CDC and ASHRAE differ. The CDC recommends 24/7. ASHRAE recommends 2 hours prior, 2 hours after. We're kind of going somewhere either 2 hours or 3 hours prior or after is kind of our recommendation. Being that the virus only lives 3 hours, in the airborne, after 3 hours, you're really not gaining much ventilating. You kind of hit the max what you're going to do. It's either falling out of the air or it's, died off in the air. The other thing we need to look at is economizers. So if we're doing a new system, this is going to kind of gear which direction we're going to go on some of our system selections. So if I have an air side economizer, I get 2 benefits out of it. I can run up to 100% outdoor air because of the ventilation. And when I'm running, if I'm in economizer mode, I am running 100% outdoor air. And so therefore I'm getting full flush through my building. The other thing is if I have an outbreak and I want to flush my building, but it's not the appropriate temperature, I can still ignore the temperature and still flush the building because I have control to go at 100%. A lot of our higher office building, or if I have a 20-story office building, normally that's going to be a water side system, and I'm going to have a water side economizer, so I'm going to get my free cooling through the water. The limitation there is that I'm no longer going to get the benefit of the air side. So I'm going to be capped out probably somewhere around 15 or 20% ventilation, so I'm not going to be able to just crank it up. So that's kind of the drawback. So as we pick new systems for buildings, as we're doing new designs, this could very well steer which type of system we're going to go after. So if we take this first step and we go, we start off with our base case example at 15% outdoor air, and say on this particular given day, say it's 80 degrees, and at 80 degrees, I can make it to 30% outdoor air at that moment in time, for example, that drops our energy down, our pass-through rate from 75.6 down to 62.5% pass-through. So now I've captured roughly 38% of the virus particles coming through here, 37.5% of the virus particles coming through, rather than at 25%. So I'm starting to capture a little bit more virus particles. Again, that's happening 4 to 6 times an hour. Now, if I was able to get up to 50% outdoor air, that would capture even more. So the higher, if day like today, I probably could go to 50% outdoor air, possibly higher. So I would be able to, exhaust even more virus particles and dilute it even more, and so that would increase our or decrease our pass-through rate on our system. obviously we're going to be limited by capacity. So roughly 1,000 CFM equals about 5 tons of air conditioning. So I can't just unlimited add the air on there. So we would have to look at the capacity of the equipment. Do we increase the capacity on new systems? Things like that. We have to look at installed costs, obviously, the energy costs. If we're in the DC market, you have to report your energy usage every year, so that if you're buying or renting a space, you have comparable energy numbers. If we have a central system, we have to look at how I actually get that ventilation to the space. So if I have a single zone system, I bring air into the building, into that unit, it goes to the space. If I have a VAV system, now I have a damper downstream of that unit that's going to vary the amount of outdoor air or the amount of air going to my space. And so we have to look at control strategies to make sure we keep those VAV boxes open as much as possible. And there's 2 scenarios. One is you increase the minimums, which then can lead to some overcooling and some reheat running, which again eats up a little more energy. Or the other option is you increase the discharge temperature. So instead of being 55, you raise it to maybe 60 degrees. So it takes longer for those VAV boxes to satisfy the space. And so we deliver a little bit more air. If you have a building, maybe a school building or something like that with operable windows, that's very effective also. So the longer you can leave those windows open and get natural ventilation through your space, that's also going to be very effective. Any questions on ventilation? I know some chat came up. Yeah, so these are going to affect the energy. Obviously, we have a slide a little later on that's going to hit the energy usage on this, but it's kind of a trade-off right now.
Will the ventilation rates be noticeable to the average occupant, like the increase in rates that you're showing?
If you can push, what can happen during the summer is you can start to lose a little bit of control of the humidity because we're going to be focused mainly on the temperature. And then also if you're running the VAV boxes, if you have a VAV system and you start running either the minimums higher, you might overcool the space. So you are going to have the possibility of making some trade-offs for comfort. But there's some other ways to address that down the road. If we get into air standardization, we can do things to reduce that ventilation back down. And that's actually what we've done in our buildings. So depending on how far you want to push it, you're going to make trade-offs on ventilation versus comfort. Oops, sorry. So next step is going to be filtration. So the first one we were going to do was dilute. Now we're going to try and filter out the contaminants. So our goal here is to pull out as many as we can. All right, again, we start off with our typical MERV 8 filter, and we're going to review the system and the static to see what level filter we can get to. So as I increase my MERV rating of my filter, it's going to capture more items. There's going to be more resistance, and that's going to be more static on the system. So we have to look at how much ductwork there is, how big the fan is, how much cushion in that system there is to add more filter. We're going to use a little bit more energy because of that static. It's going to be, we got to make sure we have enough horsepower to do it. ASHRAE and CDC both made initial recommendations of MERV 13. The way they've made that recommendation, though, is that's kind of a goal line, but they both say if you can't get to MERV 13, go as far as you can. So if you can get to MERV 11, we'll go to MERV 11. It's better than your MERV 8. If you can get to MERV 14, if you can get past it and get to MERV 14 or 15, well, go ahead, go to 14 or 15 because it's going to capture even more. So they give you the MERV 13 goal, but the farther you can get, the better off you are. And this is kind of why they gave it to you. So if you look at this chart on the right, here's our MERV 8. And again, it's capturing about 11% of our viruses. And then if we get down to a MERV 13, it's capturing 46%. So it's capturing more than 4 times the number of virus particles. Now this study, they didn't hit all of them, but what we've been seeing is that you can get to a MERV 14 and it does most of this gap between the 46 and the 71, but there's not a huge resistance drop going between those two. And some of them, we were dealing with one provider for an office building in DC, and it was basically $1 difference between the MERV 13 and MERV 14s, and there was virtually no difference in the static drop on them. So we made a recommendation that they upgrade those even further. So the MERV filters go from 1 to 20, and that's over here on the right, I'm sorry, on the left. And you can see, if you're at your house, you got a spun fiberglass, you're probably down here in this MERV 4 range, 4 to 6 in that range somewhere. So as you go pleated, you go from 6 to 8, and then it goes up from there. And they will, if you go Home Depot or Lowe's, they are labeled. It's not, you really have to hunt a little bit because it's a lot more marketing information on there before you find the MERV rating. People will ask us about HEPA filters. Why not just put HEPA filters anywhere? Well, it goes back to the original statement a little bit about the resistance on those filters. So if you put in a HEPA filter, it's a very large filter. It's not practical in most applications. Hospitals, for example, don't use it throughout the hospital. They use it in their ICU and their surgery spaces, some lab spaces, things like that. But throughout the hospital, they're using like MERV 15, things like that. So on the HEPA, the cost, the size, the static drop really kind of prohibits it from being everywhere. We may have spot locations that we might look at using it, but everywhere it's kind of a limited item. So if we take that MERV 13 and we put it in our sample system here, and we're still going to run our 30% outdoor air because we're going to add our solutions together. So we stay with on that particular day, we run 30%. And now I've gone from that 11% capture of the MERV 8 to this 46 of the MERV 13. You can see this makes a huge difference because now I'm down to a 38% pass-through rate, which means I've captured 62% of the virus particles overall between the outdoor air diluting them and then the filter actually capturing them. So 4 to 6 times an hour, we're pulling out 62% of the virus particles. So you can see, and this is actually graphically accurate, the densities here are really going down. So now that, these 2 steps that we can implement on most of our buildings fairly easily, and we can, as soon as you get the filters and get someone to program the system, you can implement these items. We've really reduced the likelihood that people inside the space are going to get to the infectious dose level, or if they do, that they're going to be a much lower viral load, so they're going to come down with a lot less severe case. Or that we've reduced the number of people that got to the infectious dose level. So these 2 are the items that are really being pushed from the HVAC side that we really recommend, the first 2 steps, and there's very little cost to these 2 items. Again, if we look at the filtration, we like to reach MERV 13. If we can go a little further, we'll go a little further. Filter costs for a MERV 13 are going to be roughly double the cost of a MERV 8. You're likely going to have to change that filter more often. So because it's a better filter, it's capturing more items, it's going to load up sooner. Likely somewhere about twice as often, but what we recommend is once a month you go up and check, once you put the new filters in, you check them once a month. You don't need to replace them once a month. You need to go check them and then figure out what your new schedule is. Just to replacing them is just spending money. If they're not loaded up, you don't need to replace them yet. Our larger equipment is going to be able to handle this better. So if we have smaller, bunch of little fan coils or heat pumps or things like that, or VAV boxes, we're not going to be able to get too far on the filters. Maybe we can get up to, a lot of those are going to have a 4 or 6, especially VAV MERV rating on them, and you might be able to get to 8 to 11. If we get above 5 tons or so, we'll probably get to 11 or 12. And if we get 10 tons and up, we're probably going to be able to get to 13. But basically, you need to look at each piece of equipment, the size of the equipment, the amount of ductwork, the size of the motors, and things like that, and figure out how far you can go. So our sensor equipment is going to be a little easier to do this on. We do have to be very careful about leakage or bypass. So this happens to be one of our units over here on the right-hand side. And what the blue item is in there is actually painter's tape. So what we've done is, as you've put the filter in, you tape one filter to the next filter. So that eliminates any bypass or leakage through between the filters. And actually on this one, what you don't see is we've taped the accessible end, we've taped the filter to the rack. There was actually a gap there, so we taped that, so we blocked that gap. A 1/2 inch gap in a MERV 8 system in a MERV 13 system, will reduce it down to a MERV 8 rating. So it's very important that you get these gaps all sealed off as best as possible. We do get asked about portable fan filter units. So we got two images here. One's a little more architectural version, maybe for a waiting room or something like that. And then this one's a little more industrial. These are usually used by companies after floods or fires or something like that to, to sort out the smoke and things like that. So this is a 500 CFM unit. It's very loud at 500 CFM. They're variable speed, but 500 CFM, and it's got a HEPA filter in it. We would recommend, if we compare it for this particular building here that has these filters, it's a 10-ton system, so it does roughly 4,000 CFM. So we would recommend you start with your central equipment first, and the reason is, if I'm capturing roughly half the particles with a 4,000 CFM on this system here with these MERV 13s, I'm going to address a lot more air, a lot more cost effectively than if I do it, I'm going with 500 CFM and capture all of them. So basically I'm going to capture 4 times the number of virus particles with my MERV 13s because I'm doing so much more air. Even though the HEPA is capturing all of it, it's just not capturing, it's not treating enough air unless I put in multiple units, which gets very costly and extremely noisy. So again, treat your central system first, and then look at hotspot areas or other problematic areas for your localized units. So on the cost side, so we were talking about costs earlier here in the energy. So this was done by Servidyne for Energy Star probably about 3 months ago now. Energy Star employed Servidyne to do this study for them. And basically, if you look at the DC market, you see the KBTs per square foot per year and the cost. So over here, again, for what they did in their study, which was 2 hours prior and 2 hours after for the extended period of time, and 50% additional outdoor air because you had to pick a number. It's roughly 6 cents a kilowatt, or sorry, 6 cents a square foot per year. So if we adjust that to the 3-hour recommendation we were making and doubling per our example case, it gets to 11 cents a square foot per year. Again, it's not a huge number. It's basically $110 per 1,000 square feet. So there's a little bit of money there, but again, it's not a permanent item. It's a pandemic response, so it's it's very doable. Go the other way. Any questions on filtration? Popped up the chat. I don't see anything in chat. Okay. So then we're going to get to air sanitization, and the one we're going to primarily focus on is going to be UVGI. And the goal here is going to be to actively kill the pathogens in the airstream. And again, the most widely accepted technology is the UVGI, which is an ultraviolet light. And there's a couple common options. It's upper room, which is what you'll see in the hospital waiting room. You'll see a blue light in there. That's kind of an upper room system, or in unit or in duct. So what we're looking at, there are other technologies out there, and bipolar ionization by far is very popular right now and gets brought up a lot. But there are these other, 5 or 6 other ones we've listed here. And the reason that these are not as mainstream in the engineering side is what ASHRAE and CDC both say is that there's a lack of consistency between the manufacturers on their performance, and very much a lack of peer-reviewed studies. So the UV's been around since 1910 for the water and 1950s for the air side, and because of that, there's a lot of there's double-blind studies. So they'll take a floor of a building, put UV in it, take another floor, don't put UV in it, and it shows not only that it killed off whatever pathogen they were looking to kill off, but that it also gave better health outcomes for the people on the floors that had it versus the people that didn't have it. So when we look at the studies for these other ones, the other technology, what they've done is they've done room sample studies. So they've got a 10 by 10 room, they put a pathogen, a mold or bacteria, or whatever it might be, or different ones in those rooms. They run the system for half an hour or an hour, and they say, hey, we killed off 99.8 or whatever % over that time period, which is true. But what they haven't done is they haven't exposed whole floors of buildings and done a double-blind study the same way that the UV GI has, so that they can prove that they haven't created any new health outcomes and that they're really getting the intended health outcome that they're looking at. So we're going to recommend the UVGI first and try and get that implemented. If we can't get that implemented, then we will point out this fact that the CDC and ASHRAE both said, and they both say that doesn't mean it doesn't work. It just means there's a lack of peer-reviewed studies, the larger studies on them. So that's what we're going to be looking at. If we stay with the UV and go down that road, so what it's doing is basically producing that UV, and it's going to expose the DNA or an RNA over a long enough period of time to enough dose, and it's going to break down the ladder structure and prohibit from reproducing. So the optimal wavelength is 265. The low pressure mercury, which is what we're going to use, is at 254, which is this chart over here. And basically, we'll get a 85% of the optimal effect out of that range. So that's what we're going to be looking at. And when we talk about health risks, the health risks on this, basically, if you expose it to your skin, it dies off at the upper level of dead skin cells. So we're not looking at a cancer risk or skin burn risk or anything like that. That's a different spectrum. But what we do have a risk of is eye exposure. You'll get welder's flash, which is painful and lasts a couple of days. So we want to avoid that for both the occupants and for the service personnel. So that's what we do have to look out for. So this one over here is an upper room example, and this happens to be a homeless shelter. The study was being done on, and you'll see these basically blue, looks like bug lights hanging up on the wall over here. And they have louvers in them to make sure that the light stays up in the upper room area. So when we have taller, high density spaces with higher risk people, so again, this was a homeless shelter, it's a good place to put it. Waiting rooms, cafeterias, again, emergency rooms, hospitals, emergency waiting rooms frequently have these. It's very common. Most of us have probably seen them in there. So that's the kind of space that we're going to be looking at. We can model this using visual. There are recommended densities that we want to do. However, if you can't get to that density, you can only afford 2 lights. Well, 2 lights is better than no lights. And if we did that, we would want to put them so that that light could travel as far as possible. So we would put it on 2 end walls of a longer space so that light can keep going across and expose the bacteria or mold or pathogen, whatever we might be looking at that time, to that UV light. The air is moving slower, so we do get a longer exposure time. So that's why this light can be a lower density light than when we're talking about an in-duct system. So our other option that we're going to look at, and this is what we're going to typically get involved with a little more frequently, because we can treat larger areas, more systems this way, is we're going to be looking at in-unit or in-duct. And so now we've increased the velocity of the air in here. It's not, in the room, it's moving relatively slowly, but in the unit or in the duct, in the unit, it's moving about 500 feet per minute, and in the duct, it's moving either 1,000 to 3,000 feet per minute. So we have to increase the intensity of this light so we can get enough exposure to make that same effect and kill off that bacteria or mold or virus. So when we do that, we're going to be looking, in this case, we put it right here. We have to look at what's in our system. The units themselves, you have to be careful. For UV stability, the duct liner, the insulation, the gaskets, the wiring, the rubber belts, things like that are not typically going to be UV stable. Your harder surface, the metals and things like that are. So we have to look at what's in there. Can we limit what's in the space that has the UV light? Can we encapsulate it with either a foil tape, or move it out of that airstream or something like that? So those items don't break down and then go airborne or something like that. Now, what's nice about this is it's going to kill off basically almost all the virus particles. So it's going to kill off 99.some-odd%. We're going to size it for what's called a single pass, so that all the virus particles are being killed off on that single pass. So if we do that, in our case here, basically our goal is to reduce all these virus particles coming through here and kill them off. We'll be able to take this outside air, and right now we're showing it's still at 30%, but what we can really do, we can leave it up there and kind of do a belt and suspenders maneuver. But in reality, we're probably going to knock that back down to our code recommended levels. We're going to leave that MERV 13 filter in there to, because it's, low cost energy item. So it's not sucking up a lot of energy, and it's going to capture the dead virus particles and pull them out of the airstream and keep the dust off of our lamps. So the lamps are doing the work. We want to try and keep them as clean as possible so that they are very effective. So again, we're going to get down to a less than 1% pass-through rate doing this. So now, all we have to worry about now is the virus particles that might be traveling across the space, affecting other people before they go through our system. But 4 to 6 times an hour, as long as we leave the fans on and the lights on, we're going to be running that through our system, and we're going to be killing off all those virus particles. So this is kind of the gold standard. We put this in place in at least 2 of our buildings, and as owner occupants. And what we're doing at that point in time is then we bring our outdoor air back down, and we are running the MERV 13 filters still. So our installed costs, so that upper room, you're looking roughly $1,000 to $2,000 for each of those lights. The starting cost for the fixture itself is around $600. So that's what you're looking at there. And then in the air handler, we're seeing roughly 50 cents to $1 a square foot. The costs were creeping up a little bit for a while there, and I think they still are. This has been a little bit of a supply chain issue, as with a lot of this stuff right now. Just manufacturing demand is very high for it. The smaller the space you have, the more likely you're going to be pushed towards that $1 a square foot. When you get into larger systems, you're going to come back down towards that 50 cents. We do have to look at bulb replacements. The bulbs do not last forever, just like any bulb. So you're roughly at 9,000, 10,000 hours. So it's every year, year and a half if you're running them full time. What we've done in our buildings is we've either tied them onto a light switch or an occupancy sensor or a time clock of some sorts. It can be done relatively simple. They're very low electrical load, so you time onto some sort of timer, and that greatly extends the run time of those lamps. And if you're only running 8, 10 hours a day because you only need to run it when you're occupied, that will greatly extend the period that you have to, before you have to replace them, because lamps are pretty expensive. Again, we do have to watch where we're putting these in. Operational costs are fairly low. I think we put in that 10-ton unit we were talking about earlier. I think it's got 3 84-watt lamps in it. And that's handling our UV for that system. Any questions on air standard? Chat. So again, that's kind of the gold standard. You do have the other system options or air sanitization options that you can look at, but this would be the one we would start with. Humidity control. So these are, now we're going to go fairly quickly through these other 3 items. They're not as big of an effect on the issue. The first 3 are really what we want to be looking at. So in humidity control, we're looking at providing unfavorable conditions for the virus or bacteria. The big concern that keeps coming up is as not only as people get pushed indoors, but also the fact of the evaporation rate. So when you get pushed indoors during the winter, it's not uncommon for our buildings in the DC area to be 15 or 20% relative humidity on our coldest days. And what that means is we're going to have a lot more of these virus particles that are going to evaporate, the coating on them is going to evaporate before it hits the surface. So now, we're only maybe 10% of them were evaporating. Now you might get 30 or 40% of them evaporating before they hit a surface. So now you're going to have a lot more virus droplet nuclei that are going to, aerosols that are going to float around. So that's why the risk, that's why the flu is more of a winter seasonal item. And, it's anticipated we're going to see similar issues with COVID-19. So that's really what we're looking at there. Where's my next table? So this is a chart that's been around for quite a while, optimal safe zone. So you can see on the viruses, the high side is not really a problem. So during the summer, if your humidity goes high, it's not big problem. It's really that evaporation rate that causes problems on the low side. But it's not a big enough risk that we're expecting to see the new standard to be that we're going to put humidifiers in everywhere. We don't see humidifiers now except for, hospitals, data centers, single family residential, something like that. But we might be looking at it for higher risk spaces, assisted living, senior centers, medical offices, or something like that. But we don't see it in our standard office buildings being the next item that we're going to look at. And it's really because it's cost prohibitive. It's very expensive. All that outdoor air you're bringing in is drying out the building. So you have to basically force air to do a phase change to get, not air to get a phase change. You have to force the water to have a phase change to go from liquid to a gas state to increase that humidity level. And that costs a lot for the equipment, costs a lot, in terms of running it, and a lot on the maintenance side. So it's not something we see changing. We do anticipate other changes are going to be the MEP 13s. We anticipate they're going to kind of become normal. We believe the ventilation rates are probably going to get increased in the next code cycles. So we do expect some other stuff, but we don't necessarily see this being a long-term change. Contaminant path. If you have the opportunity to control the contaminant path, it's a great solution. Most of the time, we don't know who the carrier is, so that's kind of our problem. If we're in a hospital or a nursing home or something like that, it's a little different story. We can supply air on the right-hand diagram over here from above and behind the nursing staff or the doctor or whoever it might be, and sweep it across the sick patient in the bed and exhaust it out or push it back to the system, clean the system. In a lobby space, you could supply air from behind the receptionist desk and sweep it out across the space and kind of keep that clean. Same thing with like a nurse's station. You could supply air behind the nurse's station and keep that air cleaner. So it's great if we happen to know, who we're trying to protect. But most of our spaces, we're looking at this one on the left. We don't know who the carrier is, and we're supplying at the ceiling, doing a lot of air turn to try and help with our air movement, which keeps our, helps us with temperature control. And we're also returning at the ceiling because that's kind of standard system now about where we can have systems and ductwork and things like that. So for displacement ventilation would be our solution. There's two solutions, and we're going to try and move the air slower, which works great if we're in so this one on the left is a cooling dominated solution. If I have perimeter heating or something like that, it doesn't work. So what I would do is I would bring the air in low and slow over here and cold, so it's going to drift across the floor. As it goes across the floor, as the heat hits either a computer or people or whatever, it's going to induce a thermal plume, so it's going to get heated up. And at that point, it's going to go up to the ceiling, so it's called our hot zone, and then get back returned through the system. So we're going to kind of capture the contaminants that way. So again, works great if I'm in a cooling dominated area and I don't have a lot of heating, or I'm not doing perimeter zones with it. But as soon as I go into heating mode, this distribution method won't work. The air comes out, goes straight to the ceiling, and also I'm not going to induce any thermal plumes with the hot air. So it kind of falls apart there. The other options kind of be taking an underfloor system and kind of migrating it into more of a laminar flow. So most underfloors still have a good amount of throw on them. But what we would do is we would put in more diffusers and larger grills, things like that, so we could slow that air down. So we would want a laminar flow by the breathing zone, so roughly 3 feet. So if you're sitting at your desk, the air is moving a lot slower at that point. So again, we can induce that thermal plume and capture it. But again, these two are not going to be something we're going to be able to commonly apply on most of our buildings. And we'll hit circadian lighting really quick. I think we got a minute or two here. So we got a lot of lighting reps telling us about how great circadian lighting is and what we can do. The goal here is basically increase the immune system. It's going to help improve your sleep patterns. There's lots of studies that show better sleep patterns equal better immune system. And they're recommending tunable LEDs to do this. Well, there's no studies out there or issue. Well, let me first go through this. So they're going to recommend the tunable LEDs, and what they're trying to do is they're trying to mimic daylighting, both the temperature of the light and the intensity of the light throughout the day to mimic the daylighting. Great in concept. The issue that we're running into is that GSA has studies that demonstrate, they have double-blind studies, well, only sort of double-blind, demonstrating that daylight improves health and performance of their staff, less sick days, less going to the doctor, higher performance levels. It was a very notable study. They did over 5 buildings in the DC area and worked out well. They were currently undergoing a study about electric circadian lighting to tunable LEDs, whether they would have the same effect. That study's not been released. I don't know how it's been affected in terms of timeline with COVID, but right now there's no studies that put all the pieces into place. The concept's out there, and we hope it will work that way, but right now there's no studies to really back it up. So what we're recommending, in terms of reopening, is that you look at, well, I guess any questions on the humidity or the tunable LEDs or anything like that? If not, in terms of what we're recommending is, engage professionals, yourselves, us, the landlord, the building engineer, get a team together, look at the short-term plan. What are we going to do immediately that we can do? If we're already in our building, what can we be doing? And that's obviously ventilation, filtration, architectural items, room limits, all that kind of stuff that everyone's already been putting in place. Oh, excuse me. So that's going to be the items were our first steps. The filters do have a bit of a lead time on them, up to 6 weeks. So depending on what type of filter and what size and that kind of stuff, that's getting better fairly quickly as the manufacturers they basically shift it from MERV 8s towards MERV 13, so they're just spending more of their time producing those. And then we're going to look at the, how you put those in effect. Make sure you get your supplies before if you can, before the people come into the building. Get your contractors, put the filters in if that's who's doing it, things like that. Look at the building set point. So it's not just a matter of, hey, I'm going to crank up the outdoor air. How am I going to do it? How am I going to make sure I maintain temperature and humidity? How am I going to make sure I get the air to the spaces? If I have VAV boxes, what are my other set points we're going to look at? Make sure we've evaluated our systems. It's not just hey, I saw this seminar, it said MERV 13s and double your outdoor air. It's not quite that simple. You do need to go through and make sure that you're not going to create new problems with your systems by doing that. If you just cranked up, you dropped in the MERV 13 filters and your system couldn't handle it, you're basically going to drop the ventilation way down because your air can't get distributed. So that becomes its own problem. So you got to be careful on that kind of stuff. So then we're going to go into your long-term plan. What air sanitization method can you do? Ideally, we would look at UVGI. Can you do that for a long-term solution? Again, it's not, most places, it's not an insurmountable cost. Again, we have a space here, 3,500 square feet, one of our spaces, and it cost us about $2,700 to do it. Again, we might be getting, fairly good pricing, but it's very doable option to look at. Are we going to look at upgrading our equipment or other changes to increase the ventilation filtration that take a little more design and construction? What are our long-term set points going to be? Then you got to get your money in place, complete that construction, and then we're going to possibly look at either balancing or commissioning the system if we've made a bunch of changes to make sure it does do what it's supposed to do and we haven't created any new issues. If you've already opened, obviously you can still implement these items. It's not a one-size-fits-all. You should look out at industry leaders. So there's there's obviously a lot of material out there. Kroger, for example, had put out a 56-page paper they put out. A lot of it was marketing based, but a lot of it had how they were addressing it. So if you're, a smaller operation or whatever, you can look, or if you're a competitor, you can look and see what they're doing to see if it's something that applies to you. Obviously, the CDC and ASHRAE. Engage experts on it. Beware the snake oil. You can go buy all sorts of little handheld UV filters and stuff off of Amazon or eBay. They're really not recommended, but you do want to, safeguard your businesses as being the next little epicenter, or your clients' businesses. Make sure they're fully protected, and find ways to get them back and working. So that is the end of our seminar. Any questions?
David, if I can just kind of emphasize a couple of things. There have been a lot of studies and discussions recently from Ernst & Young and ULI, nationally and internationally, where they're talking about the impact all of this is having on office occupancy or getting people and employees to come back to the work space. So, we've basically presented the engineering solutions, which obviously are key to making the building safe. But the other side of that is also from the architectural standpoint, which you guys obviously are experts at, from signage and social distancing. But messaging is very important. We have had clients that have called us to say, hey, come take a look at the building and tell us not only what can be done, but how do we make our occupants, our people feel safe. So having said that, these solutions can also be applied to various building types. So it's not just an office building, but restaurants or mixed use and other types of buildings can be made safer for occupancy. And as we all know, this pandemic is not going away anytime soon, and who knows what's in our future. So we'll be happy to help you answer any questions beyond this. David or myself, please feel free to reach out to us, and if we can guide you in any way, we'd be happy to. So I guess last time, are there any thoughts or questions? Please, I think you guys can unmute your mic if you have any concerns or questions. Be happy to answer.
I have a question. So with new construction, what do you see as the most cost impacting and design change for air systems for office buildings? And how do you see that affecting the energy use and things like DC BEPS and, meeting LEED Platinum and moving towards carbon neutral? And how do you see all that coming together?
So LEED's got 4.
Can you adjust your camera? We're only seeing half of your chin. So
there. Is that better? So LEED has 4. I don't know what they're not called prototypes, but they have 4 new points that are out there for discussion that you can submit under now that are related to COVID on there. And then the other thing is, so that's an opportunity there to get some points. What we would probably see on a new building or have been seeing is, discussions about, some sort of UV or air sanitization, and then the MERV 13s, and handling it that way. Possibly looking at distribution systems that could address it a little bit more. If you do the UV and the MERV 13, there's not a big hit on the energy side. The ventilation is really where you're going to, bumping that ventilation up is really where you heat up a lot of that energy.
I think there's also going to be a lot more conversation in the near future about what LEED is going to mandate, how are they going to adjust the energy requirements to have the buildings meet their thresholds. I think there's a balance. I don't think it's all one side or the other. I think there are other technologies that can also help offset some of the increased energy usages that you might be seeing through increased ventilation and filtration side, right? So you have to really take a look at all the opportunities that are available. But I can tell you that a lot of the clients that we're dealing with are concerned about it and are trying to make the changes within their, either it's a new design or even the existing buildings, by incorporating especially the UVGI lights, like David was saying, that really has minimal energy impact. And from ventilation and airflow standpoint, you are capturing or killing the viruses without having to increase their filtration or ventilation loads.
Yeah, and we've had a lot of internal discussions. It's interesting to see. We've given it quite a bit of time, many times. We've recently presented to the Maryland Restaurant Association, which then got presented to the governor's office in Maryland. And what's interesting is we've got some clients who are very much on top of it, chasing it down, pushing, they're looking at new spaces, larger spaces that they're looking at, and are pushing landlords to do things. We have other landlords that are trying to set themselves apart. We have hospital groups that are trying to look at long-term solutions. But then we have a whole nother group of, people that or users are out there, waiting it out, hoping, and only focusing on the stuff that is much more visual, to Zach saying the messaging and things like that, and with the HVAC, it's really not. So it's an interesting balance that or interesting differences we're seeing depending on our client.
Did we answer your question?
Yeah, I guess just one other follow-up question then. I think the outside air increase is something that people can relate to. Probably, you know, if it becomes a thing of the future, what is another design element that you could use to offset the increased energy use from bringing in more outside air? I'm just trying to understand, is this an envelope issue, or is it other parts of the mechanical system that need to be addressed?
Oh my goodness, that's a very good question, because yes, look, in any building, as we know, what you do to the building from minimizing heat gain or heat loss, that's the very beginning of all of that, right? The HVAC system is just trying to give you comfort within the space and bring you ventilation, right? So yeah, I mean, it's a building block of everything from starting with the building envelope, right? So we're looking at technologies, and I'm sure you guys have seen this, where you have the photochromatic glass, right? So it moves with the sun as far as the sunlight is concerned on the glass, and it darkens the glass if you've got direct sunlight, so on and so forth. So you're minimizing the energy consumption, right? So that control strategies are very important. Occupied, unoccupied site, you're going to be taking a look at that. We have a client that just finished a building here in Howard County, and it's a residential building, and they want to not only do a couple of the things that David talked about, but they want to add solar panels to the building, right? So off producing energy, offsetting, you know, what's being produced or required by additional loads. So there's a plethora of technologies that can be utilized and are being utilized. We just have to take a look at the building and sit down as a team to say, okay, what are the options, right? And what is the cost? I'm going to throw another thing at you. I mean, you know, some of these things are going to cost money, right? How do you offset it? Well, you've got utility companies that are offering rebates, BG&E, Pepco, all those guys, you know. So you have to take a full 360 approach to the resolution. The interim solution, the immediate solution, is what David has talked about. So we just, in fact, I'll give you one sidebar quick example. A local golf club down in DC called us up in a panic. They said, our membership is really concerned about, you know, how am I safe to come in the club? Well, so we went out and looked at it, and of course, you know, they don't have any ventilation that they're providing, or very minimal, right? How do you offset that? Well, you know, there are DOAS units and things like that you can put on the building to accommodate the ventilation, additional or at least minimum threshold of ventilation that's required. So there's a lot of different technologies out there, and you just have to take a look at the building and look at the owner's interest in pocketbook and say, how can we make, you know, provide the solution?
Thank you.
Of course. Any other thoughts or comments? Okay, guys. Well, thank you so much. David, I see a couple of more chats. I didn't get a chance to look at it. Do you want to look at the chat bar?
I answered one of them, yeah. I think we're good.
All right. Guys, thank you again. Like I said, David and I are available to answer any of the questions offline, and we'll be happy to, give you any input that you need to help solve your building issues from COVID standpoint, and any other opportunities that you may have that you need some help with. So thanks again, guys. Take care. We'll sign off.
Thank you.
Thank you. Thanks very much.
Of course.